Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, so let us begin with today's lecture. We will start recalling what we had done last time. We looked at what is called the orthonormal basis of a vector space, and then we looked at, so orthonormal basis was defined as a basis such that so non-zero vectors such that they mutually orthogonal and form a basis. So orthonormal basis is a set of vectors which is a basis and any two are mutually orthogonal. And then we proved a result that if a set of vectors is orthogonal and of course none of them is 0, then that is linearly independent. The advantage of a orthonormal basis was that given any vector x in the vector space, you can immediately write down those scalars alpha 1, alpha 2, alpha n such that x is a linear combination of the basis elements. So those scalars come out to be the dot product or the inner product of x with u1, x with u2 and so on. So coordinates of a vector are immediately known once you have a orthonormal basis. So that was the advantage. And then we saw the process of constructing orthonormal basis. So given a set V1, V2, Vk, if its basis well and good, even if not, if it is a spanning set, that is good enough. We can construct a set of vectors which is orthonormal and will give the same span as that of V1, V2, Vk. So the first step is if there are any 0 vectors in this, drop them, because anyway they are not going to contribute anything in spanning. And next we define by inductively W1 to be V1 and define W2 to be the next vector V2 minus the projection of V2 on W1. So that projection is removed so that the difference is orthogonal to W1. So that is the next stage V2. At every stage we go on removing the projections onto the previous ones which are defined. So having defined W1, W2, Wj minus 1, and if there are any zeros we drop them. So we are assuming that none of them is 0 once you have reached this stage. Then look at the next vector which is Vj from the given set and look at these projections of Vj on each one of the previous ones. All these are removed. You will get a vector Wj which is perpendicular, which is orthogonal to all the previous ones. So continue this process till you have finished all the vectors V1, V2, Vk. Once you have finished, you will get a set of vectors, some W1, W2, Wj, which will be orthogonal, right? None of them will be 0 and which will span the same space as that of this. Once you have gotten that, you normalize them to form a orthonormal basis. So that is the process of constructing a orthonormal basis from a given one, and we had looked at examples of that. So we will continue with the further ideas. We also proved what is called Bessel's inequality, which said that if you are given a orthonormal set, not necessarily a basis, then the coefficients V ul square, this sum is always less than or equal to norm of u square, and equality holds here if and only if these form a orthonormal basis. So that is what is called Parseval's identity. So Bessel's inequality becomes equality if and only if the given set of orthonormal vectors is a basis also. Now let us look at, if you recall, we looked at linear transformations as the maps from one vector space to another, or R2 to R2 or R2 to other things, such that they preserve collinearity, they take lines to lines. Now, on vector spaces we also have the notion of inner product, because they are all vector spaces are subsets of some Rn. So, there is a notion of dot product. So, we would like to specialize those linear transformations which not only preserve collinearity, also preserves angles, right? They do not change the angle. So, such things are called isometries. So, a linear transformation from V to V is called an isometry if the inner product of TV and TW is same as the inner product of the original. So, it preserves the inner product, and we have seen that the inner product is related to the notion of angle and distance. So, it is not surprising that we have a theorem, namely T is an isometry if and only if it preserves the length also, right. So, here we said it preserves the inner product. So, inner product is related basically to angle. So, it says T is an isometry if and only if it preserves the notion of distance also, the magnitude of the vectors is kept intact. So, a isometry takes lines to lines, right, preserves angles as well as preserves the magnitudes. So, they are sort of the perfect transformations in the planes. For example, when you physically do something, physically you move an object, the shape of the object does not change, right. That means all the straight lines remain straight lines, angles remain same, right, and the distances remain same. So, those are basically called the rigid motions of in R3. So, so this is coming from that. Translation is not a linear transformation, but still it is a rigid motion. Okay. So, this is how they arise algebraically. Isometry is a map from the vector space V to V such that it preserves of course the angle that is given, and we are saying it is equivalent to saying that it preserves also the magnitude. And this is not very difficult to show. Basically, how is the magnitude related to the inner product, that is square root of the V dot V, right, that is a magnitude. So, using that one can easily prove. So, let us say first T is an isometry, that means it preserves inner product. Then look at the norm of Tu square, by definition it is Tu comma Tu inner product, but T preserves inner product. So, that is same as U comma U, inner product of U comma U. So, if T is an isometry, if it preserves inner product, then it also preserves the this should be square here, U comma U, that should be Tu square. So, it preserves the distance magnitude also. So, that is one way. Conversely, let us suppose T has the property that it preserves the magnitudes. We want to show it also preserves the angles, it also preserves inner product. So, for that let us look at T of U plus, take any two vectors U and W, look at the sum and look at image of Tu plus W and its inner product with itself. Now, we will T is linear. So, this will be Tu plus Tw, this also will be Tu plus Tw. Use the property of that the dot product is linear in both, expand, you will get these 4 terms, right. So, 2 of them are common. So, it gives you U comma U inner product plus 2 times Tu, Tw and Ww inner product. But T is an isometry, right. So, since okay, not T is an isometry, one should actually, but what is this equal to? Tu comma Tw, right. So, that is equal to, expand that. So, from these two what you get? See, norm is preserved, right. So, what do you get? So, from 1 and 2, this is, see what we are assuming is Tv preserves the notion of distance, right. So, norm of Tv square is same as, so this is what is the norm of Tv square, right. So, that is equal to this. So, this is norm of u square, this is norm of w square. So, once you expand that you will get tu, this is anyway it is simple. I think I think there is some mistake in this proof which I have written. Try to prove it yourself, okay? Because I think there is some what we are given is, suppose this is true, okay? Then what do we want to prove? That tu comma tv, right, this is equal to, this is what we want to prove, right, for any un. So, if I take this, then this is 4 terms, that is okay, but this is norm of u square and this is norm of w square. So, this is norm of, so this side gives you norm of tu, t of u plus w square is equal to norm of u square plus norm of tu tv tu and the norm of. So, what do you get? So, let us just see, if we look at t of u plus w, t of u plus w. So, that comes out to be equal to u plus 2 times tu t w plus w w, right. So, what we are given is that norm of t v is equal to norm of v for every v. So, that is given to us. So, what is this? This is norm of u square plus 2 t u t w plus norm of w square. And what is this? This is norm of t u plus, right, this one is t of w, same vector with itself. So, that is norm square, right. So, this is equal to this, this is equal to this. So, so what is this equal to? By this given property, that is norm of u plus w square, right, again by the given property. So, what is that equal to? I can write as u plus w, u plus w, right, is it okay? Norm square. So, what is that equal to? That is u plus one will give you u w u and the other will be that is 2 times u w plus w w, right, 4 terms. But now just come, so this is same as this. So, what happens? This cancels with this cancels with this 2 cancels, right. So, what you get is t u t w is equal to u w, right. So, that is what we wanted to prove. Is it clear? So, assuming that the magnitude is preserved, we just look at the dot product of t of u plus w, u plus w, t of that, right, and expand and you get the required thing, okay. So, that is what is it clear, the proof now? See the first step, okay. So, that I have just not written the earlier thing, that was equal to t u t w, right. So, when you expand, this will be t u plus 2 times this thing, right, plus w t w w, right, t of w t w, but that this is equal to this, okay, and that t w w is equal to this by the given, okay, norm of that is basically norm of t w square. So, that is equal to same as this, okay. On the other hand, if you expand, use that property, given property and expand, you get these 2 equations and that gives you this is equal to this, okay. Expanding 2 different ways, that is all, nothing more than that, okay. So, that shows that if T is an isometry that it preserves inner product, then it also preserves the magnitude of the vectors. Okay. So, let us look at some examples which are quite obvious, which are we normally use actually in rigid motions, what is called. So, consider the map from R to R. R is a vector space over itself, right, addition, scalar multiplication. So, look at alpha times, that is a magnification in R. Okay. So, the claim is this is a linear map, obviously, right. If T of x plus y is alpha times x plus y, so T is a linear map. Okay. Claim is that it is a, we want to find out for what alpha it is an isometry. So, if it is an isometry, what should happen? Norm of Tx must be equal to norm of x, but what is norm of what is Tx? That is alpha x. So, you get mod alpha times, right, absolute value of x must be equal to absolute value of x. So, that we want for all x, right. So, that will happen if and only if mod alpha is equal to 1. So, the simple example that scalar multiplication by alpha is isometry if and only if mod alpha is, it has to preserve distance, right. So, it can't be anything else. Let us look at another one in plane R2 to R2. So, T of x y is x cos theta plus y sin theta minus x sin theta plus. Do you recognize this? We had looked at this example when we looked at matrix multiplication as a linear transformation, right. So, it is matrix multiplication by the matrix. What is that matrix? Cos theta sin theta, right, minus sin theta cos theta. So, if I look at where theta is fixed, we want to check whether it is an isometry or not. So, let us look at T of x y is equal to this thing, right. So, let us compute what is the norm of this magnitude of this vector. So, what is the magnitude of this vector? X cos theta plus y sin theta square plus minus x sin theta plus y cos theta whole thing square, that is the norm square. So, let us compute that and simplify, right, and usual properties of sin theta cos theta gives you that norm of T x square is equal to norm of x square, right. That means T is an isometry. So, that condition that preserving inner product is equivalent to preserving distance or magnitude, you can use either of them to prove something in isometry or not. So, here computing the distance is easy, norm is easy. So, we use that property, right, and that as I said was a rotation, right. So, rotation does not change the magnitude of something, right. So, as expected, so that is an isometry. And rotation in R2, R3 also is actually isometry, right. What about okay, translations are not linear, so we can't call them isometry, but they are called rigid motions. What about reflection in R2? If we take a line and reflect as if that is a mirror, every point is reflected, not necessarily x axis or y axis, but any line. So, physically it should not change, right, angle or distance, right. So, you can try that. What should be called as a reflection? How do you define a reflection in plane R2 to R2? What should be the formula for that, right? What should be a formula for reflection against a line? It will depend on what is that line. The line will have an angle theta, right. So, the formula will come out in terms of theta again. Okay. So, see in R2 x y goes to its reflection against a line of slope theta, right, angle theta. What should be the coordinates of the image point? You can take it as a good exercise and then show that it is an isometry. Okay. Physically it looks okay, it should be. It does not change angles, it does not change distances, magnitudes, right. So, try that. So, here is a once we have said that we have got a inner product space. Means what is the inner product space? A vector space on which inner product is there. So, all subspaces of R n, once we take the inner product also in mind, that becomes a inner product space, right. So, T is linear and B is an ordered orthonormal basis. Earlier we looked at ordered basis and looked at matrix of that, right. Now, there is an angle also available, you can have a basis which is orthonormal. So, T is a linear transformation from V to V and we have fixed an ordered orthonormal basis on V. Not only a basis, that also is orthonormal, any two vectors are perpendicular to each other and norm is 1. And let us compute the matrix of that, and the important thing is if T is an isometry, right, if and only if the column vectors of that matrix of T form a orthonormal set. So, given any linear transformation, given an ordered basis, you will get a matrix. So, you will get the column vectors, right. Here, if the starting basis is orthonormal, right, and if T is isometry, one can show that the column vectors are actually orthonormal. They are perpendicular to each other and norm is equal to 1, right. So, that is a special property of linear transformation when you get their matrix with respect to ordered orthonormal basis, right. So, we will not write the proof of that, but it is very nice property. And another one is the row vectors also form, why only, right, column vectors or row vectors also form, okay, an orthonormal, right. So, it says that if T is a linear transformation from one vector space to another, you take a ordered orthonormal basis of V, look at the matrix corresponding to that, then T is an isometry if and only if the column vectors are orthonormal and equivalently row vectors are also orthonormal, right. So, let us observe, we will assume this theorem, but let us see what are the consequences. So, let us write the matrix A, its column, this is some extra thing has come. A being column vectors are C1, C1 should have been here actually, okay, typo. So, let us A is a matrix whose column vectors are C1, C2, Cn, right. A matrix can be written as the columns only. Then what is A transpose A? Columns transpose will give you the rows, right. So, what is this? This is just C I transpose C j, column multiplied by the row multiplied by column, right, multiplication. So, that means A transpose A is just C I C j inner product. Remember what was the inner product in terms of vector notation? A dot B inner product was A transpose, right, B, as if you multiply as vectors, right, multiplication as vectors. So, here if you multiply, so that is a dot product. So, and if these are orthogonal, what will happen? They will be either 0 or 1 depending on I is equal to j or not, right. So, that says that if T is an isometry, right, and if you write its matrix with respect to ordered orthonormal basis, then it has the property that A transpose A is equal to 0 if I is not equal to, that means what? It is identity matrix. What is this matrix then? If these are orthogonal, right, it is 0 when I is not equal to j and equal to 1 if when I is equal to j, that is identity matrix, right. So, for an isometry, its matrix representation with respect to ordered orthonormal basis has the property that A transpose A is equal to identity, right. So, let us give that as a name, matrices which have that property A transpose A is identity, let us call them a name. We say that a matrix is called orthogonal if the column vectors form a, right, form a orthonormal set in E, that is same as saying A transpose A is equal to identity, right. So, matrices which have that property, square matrices which have the property A transpose A is identity, we will call them as orthonormal orthogonal matrices. So, the matrix of an isometry is a orthogonal matrix, right. So, you can rewrite this theorem that T is an isometry if and only if its matrix is a orthogonal matrix, right. But saying the row vectors, that is same as saying not only A transpose A is identity, A transpose also is identity, right, both are same. So, this is an equivalent way of saying that a matrix A is orthogonal if and only if, this is the definition, right. But you can take the transpose of this. What is the transpose of this? That will be precisely A transpose transpose, right, that is precisely this. So, saying that a matrix is orthogonal is equivalent to saying A transpose A is equal to identity, or A transpose, that is same as saying A transpose is the inverse. The transpose of the matrix is itself is a inverse of the matrix. So, if a matrix is orthogonal, it is invertible as a consequence obviously, right, and its inverse is the transpose. So, they become very nice. To compute the inverse, you do not have to go to determinant or adjoint or anything, row equivalent form, nothing. Just take the transpose, you get the inverse of the matrix. So, they are very special matrices, right, and they arise as matrix representation of isometries, right, which preserves the notion of angle and distance. So, that is what we are saying, that orthonormal matrices arise in matrix representation of isometries with respect to orthonormal basis, right.